Welcome everyone to today's webinar, Masonry Design in RISA. Today we're going to be taking a look at RISA 3D version 11.0.2 for the Masonry design. And I'd like to start out by addressing something. I've gotten some questions periodically in technical support about RISA Masonry. It's a program that we used to have. Some of you may have it. It's an older program. It's been discontinued, but when we originally introduced Masonry design into RISA, it was in the form of a separate program. But back in RISA 3D version 8.0, we actually rolled all of the Masonry design into RISA 3D and discontinued that separate product. So now those of you who have RISA 3D or even RISA 2D already have the Masonry design, and it's been in the program for some time now. And so today I'd like to introduce you to some of the capabilities of it. So for those of you who haven't ever looked at it before, you'll get the hang of it. And for those of you who have used it somewhat, maybe you'll learn something about the more advanced features of the Masonry design within the program. So today I'm going to show you what we're going to talk about here. We're going to take a look at wall panels. Now, I did a webinar recently on walls, and if you haven't seen that one, it's a good introduction to understanding how walls work within the program and how they compare against plates and how they work with the finite element analysis. As you can see, we're going to cover both in-plane and out-of-plane design for both ASD and Strength, and I'm going to talk about wall stiffness as being a very important aspect of the program, and we're going to talk about the Masonry design rules. This is how you set exactly how your design is going to occur for your Masonry wall. So to begin with, let's just talk about wall analysis for a moment. In the most recent walls webinar, we talked about how walls compare against plates. And what you can see here is that traditionally, if I wanted to model a Masonry wall, what I would have to do is come in and model a series of plate elements, and I would have to submesh those down into a reasonably small mesh size so that I could get accurate results. By omitting plates in certain areas, that's how I would place openings. And what this would allow me to do is get forces and stresses within the plates, and then I would have to take those forces and stresses and sort of come up with a design by hand to figure out exactly what I needed. Of course, when it comes to masonry, things like outright stress within elements here aren't very useful for us for design. Of course, there is allowable stress design, but that's based more so off of getting a bending stress or an axial stress or a shear stress. And none of those are going to be directly reported by the plate elements. But what we can do instead of modeling plates is we can model a wall panel. And a wall panel is a basic element where I just click 4 points to define it, and then I can add openings anywhere within it. And when I place an opening, it will automatically apply that to the mesh that's occurring behind the scenes. And what you'll see here is that the results for the wall and the plates are very comparable. Right here, I just put up a stress contour as an example. You'll see some slight variations here, but all in all, you're going to get about the same design, actually a little bit more accurate in terms of forces by using walls instead of plates. Now, within a wall, what we do is we define regions. And you can think of this sort of like in masonry design, where you define your full height piers and you design everything for these full height piers. Well, when you model a wall, we pick out where each full height pier or region in this case exists, and we automatically create that as its own sub-entity of the wall. So we have one wall consisting of 4 regions and 1 opening here. And what you'll see is I have 2 regions in this wall that are full height, and so they go top to bottom, and those are R1 and R4. And then I have 2 other regions which are above and below the openings, and in this wall those ones are titled R2 and R3. Now when you're going to get your design in this wall, you need to figure out how exactly these regions are going to behave. Now in terms of out-of-plane design, what we're going to be doing is we're going to be considering everything to span in the vertical direction. So note that with R1 and R4, regardless of anything, those are always going to span vertically. What does this mean? This means that for out-of-plane loads on the wall, you can think of that like a wind load hitting the face of the wall. When we get bending in the wall, we're assuming that that bending is occurring about the horizontal axis. And of course, if it's bending about the horizontal axis, then we need rebar in the vertical direction. So the program is always going to design the rebar in the vertical direction for out-of-plane forces. Now note that this does mean that if there's any horizontal bending that is bending about the vertical axis, that is going to be ignored for the rebar and code checking within the program. So if you have a wall where you've got significant bending about the horizontal axis, about the vertical axis where the wall is spanning horizontally, that is something that you're going to need to investigate by hand and address. But for most wall situations where you've got a foundation at the base and a floor level or a roof diaphragm or the such at the top, this vertical spanning is correct. And that's what we wanted to get this in for in the program, was to be able to handle basic shear wall type of configurations. Now, as for the regions above and below the openings, there's two different ways to treat them. One way to treat it would be to say that the diaphragm in this case is fairly rigid and that the lintel is also fairly rigid out of plane, in which case we would consider this top region, R2, to be spanning vertically. And you could say the same thing down below, assuming that there's a decent amount of rigidity right at the sill of this window. Now, otherwise, if we don't have that rigidity and we don't want that design, what we can do is we can tell the program to transfer the forces from the regions above and below the opening to the neighboring full height regions. And so what will happen here is that this region right here and this region right here will end up horizontally spanning as opposed to vertically spanning. And that'll allow us to ignore the design of this region and basically just treat it as a transfer element to transfer forces from this region to that one and vice versa. So it'll still exist in terms of our load attribution, but it'll be handled a little bit differently. And we'll take a look at how that works within the program. As far as in-plane design goes for masonry walls, what we do is we consider the region to basically be a beam. And so this full height pier or region is treated as a beam, where if I cut this horizontal cross section, what you'll see is essentially I have top and bottom rebar. And so these two number 5s on this side, you could picture almost like a top rebar and a bottom rebar on this side for a beam of depth this much. Whatever the width of that region is, that would be the depth of the beam. And this is called your boundary zone right here. And so with masonry design for in-plane forces, we consider that there is a boundary zone on each end of the region, and that all the bending is taken up by the reinforcing that is put right at the end there. So in this case, for in-plane design, any rebar that's in the middle of this region is going to be ignored, and instead, for this bending moment we have, we're only going to take a look at the rebar that's at the ends of the wall. And right here, we show for this particular wall design, on this side, we need two number 5s. So the last two cells, or the outer two cells of this wall, have to be grouted with a number 5 bar in each. Now note that the region over here on the left, this one only has one number 5, so we don't have as much rebar to handle in-plane design, which is understandable. And then, of course, for the shear, because if we treat this as a beam, we also need to consider the shear concepts. We also may need to place horizontal rebar in the wall. And so in this case, we have number 5s at 22 on center, here number 5s at 44 on center. And so you can think of this almost like stirrups in the beam. And so in this case, if the shear capacity of the plain masonry and the grout isn't enough, we'll come in and specify some horizontal bars as well. With respect to out-of-plane design, this concerns all the rebar that's in the middle portion of the wall, so away from the ends where we have the boundary zones. So all of our out-of-plane forces, that is the force such as a wind load that's blowing into the page right here, are handled by bending, assuming a very wide beam with a very shallow depth. So in the case of this wall, we have a nominal 10-inch thick wall, and as you can see from the cross-section here, the way we're resisting that out-of-plane bending is by placing rebar centered, so you can think of this as a beam with a depth of 4.8 inches here.
That was it.
And we grout and space the bars in the wall together at a close enough spacing so that there's enough moment capacity out of plane to handle those forces. Next, I'm going to talk about the wall design rules. So this is a spreadsheet that's within the program, and this is where we specify everything there is to know about walls. Now, I know this is a big, messy screen right here, and the reason why I'm showing this to you is to point out how many different parameters you can specify within masonry walls. And we're going to go now and take a look at each one of those. So to start with, when you open up the wall panel design rules spreadsheet, what you'll see is that there's a tab here for unity check. And this is where we define the label for the design rule. By default, all new models you create will have a wall design rule that's just called typical. And so this would be assumed to apply to all the walls that are within your model. But you can add additional design rules to define different wall types. So maybe you have interior walls and exterior walls, and you want to have a different wall thickness and different reinforcing and such between the interior and exterior. Well, then you would create two different wall design rules, one called interior and exterior, and assign those to the walls appropriately. And any given wall that you've created in your model will be designed according to the design rule that it's been assigned to. Now, within the design rules, you can specify a max bending check and a maximum shear check. When the program goes in to design the wall for bending or for shear, what it's going to do is it's going to create a unity check. In the case of bending, it'll do a unity check for the maximum combined bending and axial force. And then for the shear, this will be for the shear force within the wall. And so for this unity check right in here, as you can see with the value of 1.0, what this means is that the program will optimize the rebar and everything within the program in order to get a check of 1.0 for each one of these. So in other words, it will design it right up to the absolute limit of force divided by capacity. Now this is as compared to the setting this to a lower value. Maybe if I put the bending down at, say, 0.9, then what would happen is the program would optimize my rebar so that I got a code check that was no higher than 90% of the wall capacity. Next, I'd like to come in here and take a look at the Masonry Wall tab within the design rules. And so under the Masonry Wall tab, what you'll see here is we can set some general parameters that affect the overall masonry wall. In here, we can set the block nominal width, the block grouting, reinforcing, and the wall area method. Now, of course, the block nominal width is what it sounds like. Whenever we design a masonry wall within RISA, we're doing CMU. And so there's standard sizes on all of those CMUs that you can choose within the program for your design. For the block grouting, you can choose ungrouted, partial, or fully grouted. Now, ungrouted is exactly what it sounds like. This would basically be an unreinforced wall. Fully grouted means that all cells are grouted, whether or not they have rebar. And partial grouting means that only the cells that have rebar in them will be grouted. Reinforcing allows you to check this on and off, so if you have an unreinforced masonry wall, you can get a design for that as well. And then the wall area method. This one causes some confusion occasionally. There are two different published tables which show what the net area of a partially grouted wall is. One of those is the NCMA tables, and those tables assume that the mortar in the wall has only been applied to the face shells of the masonry units. So it assumes there's no mortar whatsoever in the webs in between the two face shells of the masonry units. Now there's also the Reinforced Masonry Engineering Handbook, the RMEH, and the tables within that assume that there's a full mortar bed. So mortar's been laid down on both the face shells and the webs of your CMU. Now if you have an existing wall and you don't know what the condition is, or if you're designing a new wall and you're not going to specify whether or not you want mortar to be placed on the webs or not, it's always conservative to use the NCMA tables. So the NCMA is on here by default, but of course you can set that Reinforced Masonry Engineering Handbook setting at any time. Next, under the Masonry In, this is the in-plane tab of the Masonry design rules. So this controls all of our in-plane design. And what you can see here is that you can set bar sizes. So the program is not going to be able to optimize for both the number of bars you need and the size of bars you need. That optimization is very difficult to do. And so what we ask for you is that you specify a required bar size, and then the program will come up with the spacing or number of bars that are required in that case. And so you can specify both the vertical bars and the horizontal bars. Now the boundary zone, that's that zone that I mentioned that's at either end of the full height wall regions. And so you've got multiple cells that are grouted on each side, and in this case we can say an 8-inch is the minimum boundary zone width, with all cells being a nominal 8-inch in width. if we have this, this means that there needs to be at least one cell that's grouted, and then we can go all the way up to 40 in this case. This is just the example setting I have here. You can set this at whatever you like. And with 40, this means that we can have up to 5 cells grouted on either side. So the boundary zone is a full 40 inches wide. You can also specify whether you want 1 or 2 bars per cell, and that'll determine whether these boundary zone bars are centered or whether they're set on each face. Now, next we have the 1.5 shear increase factor. This is also one that's caused some confusion. This is a shear stress increase factor for seismic. And in the 2006 IBC, which was one of the first codes that we implemented within the program, the code mentions that for all walls that are in seismic design category D or higher, you need to have a 50% increase on the shear stresses of your wall. And so that's going to cause a lot of overstress, and that's meant to make things very conservative for shear. In subsequent codes, they have now removed that requirement directly for seismic design category D walls. But what they have done is they've now placed that as a requirement for the special reinforced masonry wall. Now, I'd like to point out that within the program, we do not do any special reinforced walls or intermediate reinforced walls. We're only doing ordinary reinforced walls. And so in this case, the 1.5 shear factor isn't required if you're doing an ordinary reinforced shear wall. If you need to do an intermediate or special reinforced shear wall, the design that the program gives you may not encompass all of the detailing requirements. So certain things like minimum spacings of bars and such are not currently handled within the program, although eventually we do plan to put that seismic detailing in. But in the meantime, if you choose to, you can at least get that 1.5 shear increase factor for seismic if you like by checking this box. Now we also have this transfer load checkbox, and this transfer load checkbox, if you have it checked, means that there will be no boundary zones specified for the non-full height regions. Let me step back for just a second to show you what I mean. In this case of this wall that I'm showing here for in-plane design, this is moments within the plane of the wall, I'm getting design for these 2 full height regions here, but then I'm also not going to get any design for the regions above or below the opening. And what will happen is the in-plane forces will transfer as an axial force through this region and this region, such that these 2 regions will carry all of the in-plane forces in the wall, as opposed to sharing some with these, and that relates to the sort of overturning style bending. I'm getting a little bit of noise in the background. I'm not sure if maybe somebody's not muted correctly in here, so if you don't have your phone set to mute, please do. I'm not sure what's going on with that. What I'd like to do next is cover the out-of-plane masonry design. And so in this case, we have an out-of-plane design rule, wall design rule. And what we can set in here are very similar things to what we set for the in-plane. So under bar size, we can set a bar size for the vertical bars that are handling that out-of-plane design. For bar spacing, we can specify a maximum and minimum spacing limitation on here. Now, of course, we can't go under 8 inches because 8 inches is the cell width, but we can go up to 72 inches apart between vertical bars. This will apply for where the masonry is placed and where the grout is placed if we have partially grouted. If the wall is set to fully grouted, then of course grout will be everywhere and will only place masonry in these cells. For bar placement, we can specify whether the bars are going to be centered, whether they're going to be set at each face of the wall, or whether they're going to be staggered between faces. And so in the case of staggered, one bar will be on, say, the front face of the wall, and then the next bar will be on the back face, so on and so forth. Under mortar type, you can set which mortar type you have, and under cement type, you can also set the cement type. This affects just a few different design parameters within the wall. And then lastly, the transfer load checkbox that we have. And so that transfer load checkbox, similar to what happens with in-plane, for the out-of-plane, if you do not want this region and this region to be designed for out-of-plane, what will happen is the program will take the tributary force for region 2, and it will move it adjacent to the full height regions, R1 and R4. So we won't get any design for this region right here, but instead it will be assumed to be sort of horizontally spanning sending those forces into the adjacent full height region. So you have control over how that's going to occur. And then lastly, we have the Masonry Lintel tab. And under the Masonry Lintel, this is where we can control the lintels on the openings. Stepping back for a moment, I'll point out in here that when you model an opening within the program, it will automatically place a lintel above that opening to handle all of the gravity forces that are coming down. Now note that lintel design is only done for vertical forces. So none of the horizontal forces that are occurring, such as an out-of-plane wind load or such, will be handled within that lintel design. It's only going to be handling these vertical gravity forces. And so coming back to the lintel design here, what we can see is we can specify a bar size, and then we can also specify how many bars per layer and how many layers we're going to have. So maybe I only want reinforcing just at the bottom of the lintel. Well, I would say one layer, but I can have several different layers of reinforcing, so those would be bars sort of stacked above each other in the vertical direction. I can call out how many bars per layer. I can call out the bearing length, which is occurring on either end of the wall. And then I can also call out the center-to-center spacing of the layers as well. That's if I have more than one layer. Distance to the bottom would be basically the bottom cover. And then for the stirrup size on here, we can actually see, in this case, I can set whatever rebar I want for that as well. All right, so let's talk now about the actual program and how this works. What I'm going to do is I am going to create a new model, and so we will come out to the desktop here and fire up RISA 3D so that we can take a look at an example model. And so within RISA 3D, the first thing I'm going to do is open up my global parameters. Under the global parameters, we can set a lot of useful things related to masonry design. One of these is, under the Solution tab, you'll see I have this box for wall optimization. So I can set my wall design, whether or not I want to have an optimization for the wall design. In this case, I'm going to set that to no, and I'm going to explain the ramifications of that as we get a look at the wall panel stiffness, which is an important topic. Next, I'm going to take a look under the Codes tab. And under the Codes tab, you'll see all of the codes that I have available to me for design. And so what we see here under masonry is my masonry design is done per the ACI 530. Now, for those of you who aren't familiar with what the ACI 530 is, that's also known as the MSJC code. So it sort of goes by this dual name. It's also known as the TMS 402, but it's all the same code in the end. And so if I scroll down, we can design using any variety of these different ACI 530s, going all the way back to 1999 up to the current 2011 code. And then we also have the old UBC 97 design set in there as well. Now, for the purposes of this initial example, what I'm going to do is design using the current version of the code, the 2011, using ASD, and that's allowable stress design. Now I'll hit OK, and let's go in and set up a masonry wall. So the first thing I'll do is I'll come in here under the Wall Design Rules spreadsheet. This is on that data entry toolbar. And under Wall Design Rules, you can see here are all these different tabs that I mentioned. Now you'll note that there are other tabs as well that we're not going to be using. Concrete wall tabs and wood wall tabs. And so these tabs, the information that's stored in them, depends on the type of wall that I draw. If I'm drawing a masonry wall, everything under the concrete and wood will be ignored, and it will only look at the masonry wall. So in this case, I'm going to go in and I'm going to design this wall using 10-inch nominal block width. We're going to go partially grouted. Of course, it'll be reinforced, and we'll use that NCMA method to be a little conservative. Under the In-Plane tab here, what I've got is number 5 bar set for both the vertical and horizontal. We're going to pick a boundary zone that has basically between 1 and 5 bars in it, because I'm going to do 1 bar per cell. We'll leave on the shear stress increase factor, but we will not have this currently set up to transfer loads out of the regions. And then under the out of plane, once again, we'll use number 5 bars, and we'll let it space at anywhere from 8 to 72 inches. The bars will be centered in the cells, and we'll just use standard type M mortar and just Portland cement for the cement type. And then the lintel as well, we'll use number 5 bars for the bending and number 4 for the shear. So this design rule is assigned as typical And I'm actually going to just change this in here to be 10-inch wall. So now, everything that's assigned under this 10-inch wall design rule will be designed using that 10-inch block nominal width. I can hit enter to create another wall design rule in here, and I'll just call this one 8-inch wall. And in this case, I'll go in and set that block nominal width to 8-inch. And actually, I will say 8-inch wall fully grouted. Now, this is just a label for myself to keep track of what that is, but as you can see, now as I draw walls, I can choose whether the wall is going to be a 10-inch or a fully grouted 8-inch. I can create as many of these wall design rules as I like. I'm going to come in and model the wall now, and so to do that, I'll come up to Draw Wall Panels, which is 2 to the right of the Draw Beams button. And under Draw Wall Panels, I can choose which wall panel design I'm going to do. Now, in the previous wall webinar, we just talked about the general walls for the most part, and those just give you the forces and stresses. But in this case, what I'd like to use is a masonry wall. And under Materials Set, I have a few different options here. These options are all coming out of the Materials spreadsheet. So if I go to my Materials spreadsheet and look under Masonry, you'll see I have a few different materials defined in here. In this case, I'm going to use the concrete material, and that would be the standard material for CMU blocks. And here you can see I've got my modulus of elasticity, my shear modulus, and then I've got my thermal loading applied in this case, or not thermal loading, my thermal expansion coefficient set at the normal one for the masonry. Under self-weight here, you see that when I click in this cell, I actually get a little red box so I can pick out anything. And so under here, under self-weight, what you can see is I can specify a uniform density for the wall, or I can tell the program to use the block and grout properties. And in this case, with the block, I'm getting 115 pounds a cubic foot of self-weight for the concrete block, and I'm assuming the grout to be 140 pounds per cubic foot. Now, this means that when the program goes and chooses how many cells are grouted, that's going to affect the self-weight of the wall. So this does become an iterative process, but ensures that we get the most accurate results. Now, under the F'(M), that's the masonry compressive strength, you can see I've got that set to 1,500 psi, and I can set my shear and flexural rebar strengths as well. And here I just have those set to 60 ksi. So everything's pretty standard for this concrete material. I'll go back to Draw New Walls, and we'll say a masonry wall, concrete material, and I'm going to use that 10-inch wall that we defined earlier. And so now, in order to draw the wall, I just need to click 4 points. And so I'm going to make this a 12-foot high wall that is 15 feet long. And so by clicking those 4 points there, I went ahead and defined that. Now, this wall at the moment is just floating out in space, and I need to tell the program how this wall is supported. And so let's assume in this case that what we've got is a strip footing down at the bottom of this wall that is meant to restrain against shear, but not against out-of-plane bending. In other words, it's going to be pinned out of plane, so the wall can pivot back and forth. And we'll assume that at the top, there's a diaphragm bracing out of plane. That's in that global Z direction. So when I double-click on the wall, this pulls up the wall panel editor. And in the wall panel editor, this is a place where I can come in and change what design rule was assigned to this wall, what material was assigned to it, but I can also put boundary conditions on the wall. So if I come up here under Create Boundary Conditions, here I can set continuous boundary conditions. So wherever I draw one of these, it's going to go along the entire edge of that wall. Here I'm going to choose a pinned boundary condition and click on the base of the wall. I'll hit OK to exit out of the wall panel editor for a moment so that you can see in this isometric view exactly what we have, and that is this bold orange or brown line. Now this line implies right here that we have continuous pin, because we have that pin symbol, all the way along the bottom of this wall. This is different from if we had a situation where we didn't want the wall supported in the middle. If this wall were, say, sitting on a pile at each corner as opposed to continuously supported by a strip footing, then what I would want to do is actually use the explicit boundary conditions. That is the kind that I use for an individual node for columns and beams and the such, and just put one of those at each end of the wall and leave the rest of the wall free in between. That would cause this wall to sort of sag between those 2 points if I applied a vertical load. But in this case, we'll assume we have this continuous strip footing supporting it, so a continuous pin boundary condition is appropriate. Now, of course, when I solve, I don't want this wall to flop over out of plane, so I need to apply a z-direction boundary condition to the top of it. To do that, I'll double-click on the wall to go back into the wall panel editor, go back to apply boundary conditions, and what I want to do in this case is apply a boundary condition for where X and Y are set to free and Z is set to reaction, and then, of course, all rotations are also set to free. So now when I hit apply and click on the top of the wall and hit OK, what you'll see is this continuous out-of-plane bracing on the wall. So this is how I would do just a very simple wall where, for out-of-plane purposes, it would be simply supported. And so we'll take care of an analysis like that. Now, if all I was trying to do is just design one individual wall, then we would be ready to go at this point to apply loads and such. But of course, in a lot of situations, you want to do more than just design a wall. You need to design an entire structure. And the stiffness of that wall is critical to the structure. This is one place where RISA 3D really excels as compared to some of the more basic masonry design programs, which consider each wall to exist sort of within its own bubble. In this case, we can look at how this wall interacts with the other elements in our structure. So in order to do that, let's assume that we're taking a look at a framing line within an existing structure where within that framing line we have both a masonry wall and a steel braced frame. So we've got basically a dual system here for resisting lateral forces. I'm going to come in here under the Draw Members, and I'm going to draw in a steel frame here. So we'll use some W10 by 30 columns, and in this case I will set these to be A992 columns. And I'm going to draw this adjacent to this existing masonry wall. And then we will come in and put in some beams as well. I'll put in a W16 by 36 beam along the top. And I'm going to put in a link beam, a W10 by 30, and that beam's going to transfer forces back and forth between the masonry wall and the steel frame. So they'll be connected up at that point. And then I'm going to put in a brace as well. And so for that, I'm actually going to come in and pull out a single angle brace. And for this single angle, we will use a 6 by 6 by 5/16. And I'm going to set this to be an Euler buckling brace. Now, what does Euler buckling mean? Well, that means that this brace is going to be more or less a tension-only brace. But what will happen is, if a compression ends up in this brace, it'll be considered acceptable as long as that compression doesn't exceed the Euler buckling capacity of the brace. In other words, as long as we know that there's just a small amount of compression that won't cause the brace to buckle, we can consider the brace to be present in the solution. Whereas if a large compression tries to go in there, the program won't let that large compression in. It will assume this brace has been buckled and it will ignore it. And then, of course, this brace will always be considered present for tension forces. So here we can sort of see a rendering of how that looks. And let me just come in and put in some boundary conditions as well. And so in order to prevent a torsional rotation instability on the columns, I'm going to put a Y rotation in addition to my pin. And then for the top of the frame, I'm just going to also restrain this in the global Z direction, so that way we don't have any instability issues here. So as you can see, I've got a steel brace frame and a concrete shear wall, and those are connected by this link beam. And we're going to consider that this is the situation within the structure. And perhaps there's some sort of decking or diaphragm up above that's transferring forces into these. But when it comes to lateral loads, at least in this global X direction, this steel frame and this masonry shear wall are going to be sharing some of the forces with each other. Now I'll go in and set up my basic load cases. And so for this, I'm going to set up 4 different basic load cases. We're going to have self-weight, we're going to have superimposed dead load, we're going to have a wind that is in plane, and a wind that is out of plane. Under self-weight, I'm going to come in here and choose dead load for the category, and that's the same for the superimposed dead as well. Maybe that represents something that's sitting up on top of this wall. For the in-plane wind, that would be wind in the global X direction. So for that category, I'm going to choose the WLX. And out-of-plane wind would be wind in the global Z direction. So for that, I'm going to set that to be the WLZ. For self-weight, of course, we want to put the -1 in Y gravity, and this is going to apply a downward acceleration of 1g to the entire model. And so then based off of the area and the density of all the materials, we're going to get a self-weight automatically applied in this case. Now, for the superimposed dead load, I'm going to come in here and draw a distributed load, and we're going to assume that that is 6 kips per foot, and that gets applied to everything. Now, note that with the distributed load, if I click on a wall panel edge, it applies that load to the entire edge of the wall panel. So I don't need to put in any beams or anything to pick up that load. You can apply distributed loads directly to the edge of a wall panel. And I'll put that on the link beam and on the brace frame beam as well. Now I'll go back to apply distributed loads, and we'll go in the global X direction for a X direction in-plane wind force of 2 kips per foot, and I'm going to apply that very similarly. So what you can see here now is there's a 2 kip per foot force dragged into the wall and these beams, and that's assumed to be coming from the overall structure. So maybe this diaphragm that we're imagining exists up here, or the roof decking or whatever it is dragging about 2,000 pounds a foot into these frames, and these are intended to resist that. And then for out-of-plane wind, let's say that maybe the wind is just going to blow right through this steel frame. We're not concerned about that. But for the wall, we'll assume that we're in a hurricane zone. Maybe we're down in Miami where we're just going to get some extreme out-of-plane wind loads, maybe 80 pounds a square foot. I'm going to come in and apply that to the wall as an out-of-plane surface load. And for that, I use this apply surface loads to wall panels, similar to the plate surface loads, but a little bit different. One of the nice things in wall surface loads is that I can specify a different magnitude in the top to bottom, so I can do a tapered surface load. This is excellent for conditions where your wind force increases or decreases over the height of the structure, and also for hydrostatic loads or soil loads if you have to model those where you have a higher load at one point than another. The program will automatically figure all those out. Now with the loads applied and the structure modeled, I can come into the load combination spreadsheet, and so I'm going to set up 2 load combinations, one called in-plane and one called out-of-plane. I'll turn on P delta for both of these because P delta is going to be required when we get into the strength design of the walls. For now, we're just doing ASD, so we don't actually need that if we don't want it. For the in-plane, I'm going to set up dead load with a factor of 1, and we'll assume that this 80 pounds a square foot wind load was created using the 2010 ASCE7. And for those of you who don't already know, for ASD, using the 2010 version of the ASCE7, my wind load factor would be 0.6, not 1.0 as it was in the old 2005 edition of that code. So I'm going to come in here and set up the correct load factors for ASD, which is 1.0 dead plus 0.6 wind in both directions. We can solve for both of those. All right, so next I'm going to go in and I am going to do a batch solution of this model, and let's just take a look at the results that we get here. So one place that I can take a look at the results is under my wall panel design spreadsheet. And in here, you'll see right now I'm on the concrete tab, but if I go to the masonry tab, I get all sorts of results reported to me right in here. But maybe a better way of looking at this would be to take a look at a detail report. So if I click on that white detail button and click on the wall, here I can get a report for this wall. Now there's only one region because I don't have any openings, so the whole wall is considered to be one pier. And in here we can see I've got my ACI 53011 ASD. Special inspection is yes. I'll give you a little hint. This is hard-coded to yes. The code always requires special inspection, so we never have that set to no within the program. Under my combined checks, what you can see here is that for my combined axial and bending stress divided by the allowable bending stress, I'm at 1.0. So I'm at right at the limit for the design of this wall in terms of the in-plane forces. And then you can see some of our other code checks here. We get the bond strength. The shear is actually over, so we're failing in shear in terms of the shear stress over allowable shear stress. And here's the forces in this wall, the axial, the shear, and the in-plane moment. So that's like the overturning moment that we would be looking at in this wall. And if I scroll down a little bit farther, we get some information on how this was all designed. So here's a bunch of things that we can use to sort of compare against the code checks to see how things are looking if we want to dig into how all these numbers came about. And what you can see is that the program's designed a 40-inch wide boundary zone on this wall. So we got 5 vertical number 5s at each end of that wall. That's a whole lot of steel going on in there. Now let's take a look at the out of plane. And in the detail report, I can just flip to out of plane up here at the top. And under out of plane, what we'll see is that for my combined check of axial and bending, I'm less than 1. But for my stress in the steel divided by the allowable steel stress, I'm over 1. So even though this program works for combined axial and bending, my rebar is going to be yielding. We're about 38% overstressed. So whatever the current design is not going to work. And if I scroll down, I can see what the current design is set at is number 5's at 72 inches on center. And so everything else is ungrouted here, as you can see, because we define this as a partially grouted wall. So this wall is clearly failing right now due to those forces that we have. Now, another thing to consider is that because we have the grouting at 72 inches on center, as opposed to more frequently, we have a lesser wall area than we would if this was fully grouted. And what the code advises you to do for the stiffness of the wall is to use something called the equivalent solid thickness. So essentially, the code says, hey, if you just collapsed out all of these void spaces within the wall and mashed this down to one equivalent solid wall, what would the width, or the thickness in this case, of that wall be? And if I scroll up here, you'll see we report an equivalent solid thickness of 3.55 inches. So in other words, this nominally 10-inch wide wall really should have the equivalent stiffness of a wall that's only about 3.5 inches wide, but is solid all throughout there, as opposed to having these voids. Well, this is very important because this affects the stiffness of the wall. When we go in and we do that finite element analysis of this wall, we're considering a bunch of individual plate elements within the wall. And so we're calling these plate elements 3.55 inches thick in order to give us our deflection that we're going to get out of the model. And that deflection not only affects, of course, just what the deflection is, but it affects how other things are treated in the model. So if we take a look, for example, with this wind force blowing on here, if I take a look at my vertical brace in this case, what we see here is that the axial force in that vertical brace is 0 kips. Now, because this is a single angle, we have a 0 kip axial force. We know that our wind is being applied in that x direction. What that really means is that this brace has buckled. So it's done its job as an oil or buckling member. But that also means that this wall tried to lean over far enough to push enough force into this brace that it ended up buckling, and so the wall ended up having to carry everything anyway. Now we see that the wall has failed, and how do we address that? Well, under the results toolbar, we have a suggested design spreadsheet. And if I come into the suggested design spreadsheet, you'll see there's a masonry walls tab, and under here, what the program says is, hey, for wall panel 1, your current spacing is 72 inches on center. That's for those vertical rebars. But the program recommends using a 48-inch spacing on the rebar. And if I right-click in this spreadsheet, I can say solve again using the suggested shapes. And what that'll do is that will now use 48-inch spacing, and with 48-inch spacing, our equivalent solid thickness changes because we have more grouted cells, so the wall stiffness changes, so all the forces are going to change. That's why we have to run another solution. Now, if I come back to this same wall, now we're using the tighter spacing on the rebar. Now it's number 5's at 48 instead of 72. And look at that. Our equivalent solid thickness went up by almost a full ½ inch in this case. We're almost 4 inches thick in terms of equivalent solid now. And if we take a look at it, now we're passing. That shear steel stress that we had that was over 1.0 is now less than 1.0. So we're fine for out of plane. And then in terms of in plane, what we've got here is everything's passing as well. And scrolling down, you can see I only need 1 bar for my boundary zone, not 5 bars for the boundary zone. That's huge. Now, another thing to note is previously, because that brace had buckled, the wall was carrying the entire lateral force. And that force, as we can see, adds up to 36 kips. So we had 36 kips of shear in this wall. But now, when I take a look at my in-plane results and I take a look at the shear, you can see the wall is only carrying 23 kips. So what happened to that other 13 kips of shear that it was previously carrying in the previous iteration? Well, if I take a look at the brace, you'll see this brace is now carrying 18 kips of axial force. In other words, because this wall was stiffer, it didn't deflect as much, so it didn't try to push as much force into this brace, and as a result, this brace never buckled. And this 18 kips of force, believe it or not, is actually below the Euler buckling capacity of a 6x6 single angle. And so in this case, we're saying, hey, the single angle can carry that 18 kips, which cuts down on the amount of force that's in this wall. And so you can see how just that difference between the rebar out of plane affecting how much the in-plane stiffness was, that was huge. That's a very big difference. And so this is something that you never really would have caught in terms of just looking at this wall by itself, as opposed to taking a look at the wall as part of a whole system. This is the big advantage of doing finite element analysis on your masonry walls, as opposed to just doing a one-off solution, or as I said earlier, it's sort of being in a bubble. So that's a big effect that's occurring on the wall right there. Next, what we're going to do is we're going to come in and take a look at the strength design provisions for this same wall. So I'm going to come into my load combination spreadsheet, and of course, if I'm going to use strength design, I need to come up to the correct strength design factors. So that's going to be 1.2 on the dead, and by using the 2010 ASCE 7, that would be 1.0 on the wind, and that's as opposed to 1.6 on the wind for previous editions of the ASCE 7. And under the codes tab, I'm going to come in here and set this to be LRFD, and we're going to do strength design on the masonry as opposed to ASD. So when we did the ASD design on this wall, what we saw was that the program compared everything in terms of stresses. What is my actual stress over my allowable stress? Well, now when I come in and do my strength design, we're going to see what the program does is it compares things based off of strength. So this is my axial force over my axial capacity, my bending force, my bending moment over my bending moment capacity, and the shear over the shear. So it's handled a little bit differently. And what we can see for this wall is that my unity checks are all fairly low for the in plane, and then for the out of plane, we're also fairly low as well. So axial details, we're only about 59% stressed axially, and for bending, only about 35% stressed. And that's with this rebar at 48 inches on center. If I go back to the suggested design spreadsheet, what we'll see here is that now the program is recommending that we go back to 72-inch spacing. In other words, ASD being more conservative in this case, we can actually cut down on the amount of rebar spacing by using strength design, so long as we're using the correct load factors in the load combination spreadsheet. Now, I could go in under the suggested design spreadsheet here, right-click and say Solve Again, but this is where I wanted to show you one of the neat tricks of the program. I mentioned how the rebar spacing affects the stiffness of the model, and the stiffness of the model, of course, affects what loads are in the model, because when we take a look at finite element analysis, the amount of force in something depends on how stiff it is. And, of course, when we take a look at the code checks in this case, or when we're determining what the rebar needs to be, the results from our solution determine what the rebar needs to be, which determines what the stiffness is. You end up in sort of a loop here where the stiffness depends on the force, but then the force also depends on the stiffness. And so to get around that in the global parameters, what we enabled was this wall design optimization. And so when I have this set to yes with 3 iterations, what the program's going to do is it's going to run a solution of my model, and from that solution it's going to pick out a necessary rebar that I need. With that necessary rebar, it now has a new stiffness for the wall. It will then apply that stiffness, resolve the model. Now, by resolving, now my forces are going to be different. Maybe it needs a different rebar arrangement. It'll put the new rebar in, adjust the stiffness again, solve the model again. And so it will solve this until it either converges, where all of my walls have the same recommended design from one solution to the next, or until I tell it to stop. And in this case, I'm going to say, go ahead and run 3 iterations. So the program's actually going to solve this whole model for a batch solution 3 different times. Each time it's going to rebuild the stiffness of that wall. So I hit Solve Batch. And you probably didn't notice in this case because it's a small model, but that can add some time, a noticeable amount of time addition to the solution. So if you see a situation where your model solved load combinations 1 through 10, and then all of a sudden you see it going back and solving load combination 1 again, you're going to say, what's going on here? that's that automatic iteration in terms of the wall design. And that ensures that your solution for what design you're getting matches the stiffness that was used for that solution. So this is just another one of those complexities that comes in when you actually start caring about what the stiffness of the wall is. In this case, the program, after running several different iterations, came up with a design for us out of plane where we're at 72 inches on center for that rebar spacing. And so we're sort of right back to where we started in that one. Now, I'm actually going to flip us back into ASD, and then what we're going to do is take a look at the lintel design. So for that, I'm going to put the load factors back to what they were before, and let's go ahead and add an opening into the wall. So under codes here, we're going to go back into the 14th edition ASD and the 2011 ASD. And I'm going to double-click on the wall, and what you'll see here in the wall panel editor is we just have one giant region on this wall. I'm going to go ahead and get rid of that by deleting it, and I am going to shut off that hatch pattern in the background so that we can see this grid. This grid will allow us to draw openings, and if I go to the bottom left corner of the wall panel editor, I can specify the increments for that grid. So I'm going to say I want 3 increments at 5 feet on center for horizontal. And for the vertical, I'm going to say I want 3 increments at 4 feet on center. This gives me a nice handy snap point to draw a 5-foot by 4-foot window right in the middle of my wall. And you'll see it automatically places a lintel there. Now, you'll note that there's no regions shown. That's all right. If there's no regions in the wall, the program will automatically generate them at the time that we begin our solution. So I'll just come in here, and what we've got now is this wall with this opening shown on it. I'm going to go back and solve a batch solution for this wall panel. And because we had that iteration turned on, it should have already come in with a final design. And so if I go to suggested design, we can see that there's nothing suggested, so the wall is perfect as is. And I'm going to come in and double-click on the wall so that we can take a look at what we've got going on here. And so here we can see, in this case, our design is showing we're actually getting an over-allowable on the shear. So the program was able to iterate it as much as possible, but it evidently still wasn't enough to be able to handle the amount of shear that's in this wall. So here we have 1.6 for our allowable shear over our actual shear. So that's causing a real problem in this case. Bending, we're getting 3 bars in the boundary zone, and this is on region 1. Let me go back and double-click on the wall so I can make this a little more clear. I know this is kind of hard to see right in here, but what we're looking at is here's the regions in the wall now that I've solved. I have 1, 2, 3, and 4. And for in-plane, you'll see that I'm actually getting a design for each one of these regions, including the regions above and below the opening. So by having this 3, number 5, that means I've got a boundary zone in this little spot above the opening. And I don't really want to detail that out. I see no reason to come in and put these bars in here. In reality, this region's only intended to just transfer the load from this side of the wall to that side of the wall. And the same is true underneath the window. So I'm going to come into the wall design rules spreadsheet. And for my masonry in plane, for that 10-inch wall that we're doing, I'm going to go ahead and say transfer load. And so we can take a look down at the bottom of the program. If you ever have any questions as to what something means, in the status bar it says down here, transfer in-plane loads from regions above and below the openings to adjacent regions. So now when I go back and solve a batch solution of this again and double-click on the wall design, what we'll see is that for in-plane now, we don't get any design above and below there. It's not detailing out any rebar. And these regions right here are intended to take that. Now for out of plane, I am getting a design, and that is number 5 at 32 inches on center all throughout the wall. And that's fine for me. Now what about the lintel? Well, when I come in and take a look at my detail report, you'll note that aside from being able to take a look at the detail report for a given region, I can also take a look at the detail report for an opening. And in the opening, we're going to get the design of the lintel here. So here's our shear and moment, and you can see that using FEA, it's almost a simply supported beam, but as you can see, due to certain load being dragged in different ways, it's not just this straight-up normal diagram that you would expect, but this is actually the most accurate diagram that you can get. And so looking in here for shear and bending, I can see that I'm failing because my unity checks are above 1.0. So here's how I detailed this lintel, 16 inches deep with 3 number 5s and number 4 stirrups at 6 1/4 inches on center. and that's evidently just not cutting it. So what we need to do is probably just make this lintel deeper. So I'm going to come back to that wall design rules spreadsheet and go to the Masonry lintel tab, and let's set that lintel to be 24 inches deep rather than 16 inches deep. And if I go back and solve the model again and take a look at the detail report for it, now we'll see that we're actually passing in this case for shear and for bending, and our design no longer requires the stirrups. That's going to save us a lot in terms of detailing for sure. And here it's just recommending that we put 3 number 5s down at the bottom of it. Now, what about that pesky problem with this wall failing for shear in terms of the in-plane force? Well, if I go back to the wall design rules spreadsheet and go to the Masonry in-plane, or go to the Masonry wall tab, I'm going to tell the program, go ahead and fully grout this. And let's see if that helps us out with our shear. I'm expecting it should help considerably. And so if I go back to the detail report now, hey, look at this. We're passing. The shear stress is right near where it needs to be for the allowable in this case. And if I double-click on the wall, now just for this one region only, it's requiring horizontal bars number 5 at 24 inches on center. And hey, that's very doable. So in this case, we've got a complete design for our wall, even with the lintel and the opening, and it's completely accurate. And so you can see everything that's involved with the design of masonry within the program here. So it's a very powerful tool, especially when you consider using this in conjunction with a larger model. In order to make this presentation simple, I just put together this very basic little frame here. You can have a model with 100 different masonry walls in it and a rigid diaphragm, and by running these iterations, the program's going to be able to figure out exactly how much force goes into each wall and exactly what you need to do for each wall. These are very valuable things to be getting out of the program.